The sun has long been a significant source of energy for us, especially in recent times, and it is about to undergo a pivotal and transformative change: the reversal of its magnetic poles. This event typically occurs at regular intervals, marking the halfway point in the solar cycle, and it has profound effects on Earth. It might surprise you to learn that the sun could rapidly become a serious hazard capable of completely disrupting life on our planet. As you'll discover, the sun's magnetic field is generated by the motion of electrically charged gases in its core, a process called the solar dynamo. Over time, this magnetic field grows more intricate and distorted due to the sun's evolving conditions and convective movements. Ultimately, this leads to a full reversal of its magnetic poles. The North Pole becomes the South Pole and vice versa. But let's take a moment to break down the entire cycle and better understand the sun. The sun is mostly composed of hydrogen and helium in the form of plasma, a state of matter where electrons are no longer bound to atoms, creating a mix of free electrons and ions. The sun's interior is divided into multiple layers, with the core at the center surrounded by the radiative zone and the convective zone. The core is where nuclear fusion takes place, converting hydrogen into helium and releasing immense amounts of energy. The radiative zone lies above the core, where energy is transferred outward through radiation. In this region, energy moves outward slowly as photons are absorbed and re-emitted by the sun's plasma. The convective zone, which is the outermost layer, is where energy is transported by convection. Hot plasma rises toward the surface, cools, and sinks again, creating currents within the sun. The solar dynamo operates primarily within the convective zone and the T-line, a thin layer between the radiative and convective zones. The T-line is crucial because it's where the sun's differential rotation and shear flows play a major role in generating the magnetic field. Here's an interesting tidbit you might not have heard. The sun doesn't rotate as a solid body. Instead, different parts of the sun rotate at varying speeds, with the equator spinning faster than the poles. This is known as differential rotation. This variation stretches and twists the sun's magnetic field lines, elongating them. The solar cycle is an approximate 11-year rhythm during which the sun's magnetic field undergoes a sequence of changes, culminating in a flip of the poles. This cycle is powered by the solar dynamo and includes several phases. At the start of the solar cycle, the sun enters a phase known as solar minimum, characterized by few sunspots and low solar activity. The magnetic field is relatively simple and consists of a clear north and south pole. As the cycle continues, sunspot activity intensifies. Sunspots are regions of intense magnetic activity, and they arise as magnetic fields from the sun's interior rise to the surface. These sunspots appear in pairs with opposite magnetic polarities and gradually move toward the sun's equator. Around the midpoint of the solar cycle, the sun reaches solar maximum, a time of peak activity, marked by the highest number of sunspots, solar flares, and coronal mass ejections, CMEs. The magnetic field becomes extremely complex and entangled due to constant twisting and shearing from differential rotation and convection. As the solar maximum subsides, the magnetic field starts to reconfigure itself. The twisted field lines reconnect, and the sun's global magnetic field gradually reverses its polarity, with the north magnetic pole becoming the south pole and vice versa. This transition is facilitated by the shifting and restructuring of solar plasma movements. After the magnetic reversal, the sun enters a period of decreasing activity, returning to solar minimum. Eventually, the magnetic field reorganizes, and the cycle starts over again. Currently, we are at the solar maximum phase, and the sun's magnetic field is on the verge of flipping. During this time, we can expect significant solar activity, which, while fascinating, could also pose serious risks. However, the sun's magnetic field reversal is not a sudden event, but rather part of a continuous cycle. As the solar cycle progresses, the sun's magnetic field undergoes various transformations. Right now, the magnetic field is at its most tangled and complex. It reaches a critical point and begins to reorganize, resulting in a pole reversal. So, how do we know when the sun's magnetic field will flip? Scientists monitor the sun's magnetic activity with a variety of instruments and methods. Observatories equipped with advanced telescopes, both on Earth and in space, provide detailed images of the sun's surface and sunspot activity. Instruments like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory track the sun's magnetic field and its changes over time. One key indicator of an impending magnetic reversal is the behavior of sunspots. During solar maximum, sunspots increase in frequency and become more prominent as they move closer to the sun's equator, signaling that the magnetic field is becoming unstable and preparing to flip. While we're on the topic, let's dive a little deeper into sunspots. When the sun's magnetic field lines become twisted and contorted due to differential rotation, the equator spins faster than the poles, causing the magnetic lines to stretch and bend. When these lines loop across the sun's surface, they suppress the convective movement of hot plasma from the sun's interior, resulting in the cooler, darker patches known as sunspots. Sunspots are not only intriguing but can also generate powerful solar flares and coronal mass ejections, CMEs. These events release vast amounts of energy and charged particles into space. If directed toward Earth, they can disrupt satellite communications, damage power grids, and pose threats to astronauts in space. Additionally, increased solar activity can amplify auroras, though it can also raise radiation levels in Earth's upper atmosphere. Now, let's explore the difference between solar flares and coronal mass ejections, CMEs. Both are massive bursts of energy from the sun, but they differ significantly. Solar flares are sudden and intense bursts of radiation caused by the release of magnetic energy from sunspots. They emit an immense amount of energy and light, often in the form of X-rays and ultraviolet radiation. Think of them as giant explosions of light and heat on the sun's surface. In contrast, coronal mass ejections, CMEs, are enormous bursts of solar wind and magnetic fields originating from the sun's outer atmosphere, the corona. These can be compared to enormous bubbles of gas and magnetic energy being propelled into space. When a CME takes place, it sends billions of tons of solar particles into space at incredibly fast velocities. Though solar flares and CMEs are related, they are distinct phenomena. A solar flare can occur without a CME, but at times, an exceptionally intense flare may be accompanied by a CME. While a solar flare doesn't always trigger a CME, they can be connected in terms of their impact. Solar flares can interfere with radio communications, disrupt navigation signals, and present significant radiation hazards to astronauts in space. In contrast, CMEs can have a more widespread and severe influence. CMEs can induce geomagnetic storms, which can interrupt electrical grids, satellite functions, and navigation systems. They can also intensify auroral displays, but they pose significant risks to Earth's technology and infrastructure. Additionally, during times of heightened solar activity, the level of radiation reaching Earth tends to rise. Satellites and other space-based devices are particularly susceptible to increased solar activity. Charged particles from the sun can damage electronic components, disrupt communication signals, and even alter the orbits of satellites. Beyond these technological risks, could there be other effects on Earth? While the reversal of the sun's magnetic field doesn't directly influence Earth's atmosphere, the resulting shifts in solar activity can have an indirect effect. Some research indicates that variations in solar radiation can affect atmospheric conditions and weather patterns. For instance, heightened solar activity may cause a slight warming of Earth's atmosphere, potentially worsening existing climate change. Could auroras be the only positive outcome we experience? Perhaps. One of the most captivating outcomes of increased solar activity is the more vivid display of auroras. These dazzling light shows happen when charged particles from the sun interact with Earth's magnetic field and atmosphere. While the aurora borealis is most often mentioned, similar auroras can be observed near the South Pole. During periods of intense solar activity, auroras become more frequent and may be visible at lower latitudes, offering spectacular visual displays. However, despite the awe-inspiring auroras, there are also more concerning aspects of the sun's magnetic reversal if we are unprepared. A major threat tied to the magnetic field flip is the heightened risk of geomagnetic storms. These storms arise when solar wind, packed with charged particles, collides with Earth's magnetic field. In extreme cases, such storms can trigger widespread blackouts and damage critical infrastructure. One significant historical event took place on the morning of September 1st, 1859. Astronomer Richard Carrington was observing the sun when he witnessed an extraordinary occurrence. At 11:18 a.m., he observed a brilliant flare of white light coming from a group of sunspots. This event, now known as the Carrington event, marked the onset of the largest geomagnetic storm ever recorded. The white light Carrington observed was the result of a colossal solar flare, a surge of radiation caused by the release of magnetic energy within the sun's environment. This flare was so powerful that it triggered an enormous CME directed toward Earth. The CME reached our planet in just 17.6 hours, an impressively short time considering the sun's distance of 93 million miles from Earth. When the CME struck Earth's magnetosphere, it initiated an intense geomagnetic storm. The impact was swift and widespread, disturbing Earth's magnetic field and generating electric currents in the ground. Telegraph lines, which were the primary form of long-distance communication at the time, were severely affected. Operators experienced electric shocks, and some telegraph stations even caught fire. Remarkably, operators were still able to send and receive messages after disconnecting their batteries, thanks to the induced electrical currents. In addition to disrupting telegraph services, the Carrington event also produced a stunning display of auroras. These bright, colorful lights were visible far beyond their typical polar regions. People as far south as the Caribbean and Mexico reported seeing brilliant auroras, with the light being so intense that it was possible to read by it. Miners in the Rocky Mountains were even said to have mistaken the light for dawn and began preparing breakfast. Now, imagine the impact if a solar storm of that magnitude were to hit Earth today. With our current reliance on satellites, communication systems, and electrical grids, the consequences could be far more severe. The sun's activity follows a cyclical pattern, and as we approach the peak of the solar cycle, the chances of such an event occurring rise. As the sun's magnetic poles prepare to reverse once again, we must remain vigilant and continue to monitor solar activity closely in order to prepare for any potential hazards.